Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutiwa Sos Ugobela Wemet. And without any further ado, let's look at these questions that we have here. Okay, so we have question 5. It says, after an emergency landing at Bloemfontein Airport, a passenger of mass 70 kg evacuates the stationary aeroplane using the evacuation slide that makes an angle of 40 degrees with the horizontal. When the passenger reaches a height of 2.8 meters above the ground, the passenger has a speed of 0.35 meters per second. So note that. So we are given the speed at which it reaches that point there. So from the beginning where our question is starting, the person has a velocity of 0.35 meters per second at a height of 2.8 meters above the ground. So as we can see, it's right there. Then 5.1 says, define the term non-conservative force. Now, what is a non-conservative force? As we know already, a non-conservative force is a force for which the work done in moving an object between 2 points depends on the path taken, right? So we say is a force for which the work done in moving an object between 2 points depends on the path taken. And that's how you would define a non-conservative force. Then we have 5.2. So above here, it says a constant frictional force acts on the passenger as it moves down the slide. So now we are being told that the slide here has friction. Then 5.2, draw a labeled free body diagram showing all the forces exerted on the passenger, 3 marks. So we know 3 marks, 3 forces. So let me just draw it right here. The dot indicating the passenger. And then now we know that perpendicular to the slide will be our normal force. And then we don't resolve our gravitational force, but we just throw it straight down. But then we know that there's friction. So friction must always oppose the motion. So there we go. We have kinetic frictional force, the normal force, and also the gravitational force. Right. So that's how you would get your 3 marks for 5.2. So now we are on 5 marks already. Then 5.3 says, name a non-conservative force acting on the passenger. Now we have already discussed that examples of non-conservative forces are your frictional forces, tension force, and applied force. Right. But then the only non-conservative force acting on the passenger as it slides down that slide is kinetic frictional force. So we'll just say frictional force. And then just like that, at this point, we are at 6 marks, right? Okay, so I'm busy talking about the marks because I want to shift your focus into having to accumulate marks. So even if you don't actually get total in a specific question, but then if you can always aim to get 60 to 70% of each and every particular question, then it's very easy to just pass your exam like that. So each and every question that you are doing, aim for at least 70% or 60% of the question, right? Then we have 5.4 says, using energy principles, calculate the velocity of the passenger at the lowest point of the slide, right, for 6 marks. Now, I normally say that when it comes to the energy principles on an incline, you normally have to use the work done by non-conservative force. Also bearing in mind that with all the statements, they've been giving us hint on the non-conservative force. If you can check 5.1, it's been saying define non-conservative force. And then if we can check, we are being told a constant frictional force. And then here they say name a non-conservative force, which is what? Frictional force. So now there's been hints that has been thrown by the examiner to say that use the work done by non-conservative force. And then remember I said that formula works best when there is height. So if you haven't seen my video on the lesson on work, energy, and power, make sure that you check it out. I will actually drop the link on this video here. The coefficient of kinetic friction of the surface is 0.112. So note that we are only given the coefficient of kinetic friction and not the actual value of friction. So we do know and understand that every time we are given the coefficient of kinetic friction, it means that we ourselves have to calculate the magnitude of the frictional force. So, okay, for 5.4, using energy principles, calculate the velocity of the passenger at the lowest point of the slide, meaning at this point, right? So now we have decided that we are going to use work done by non-conservative force. So let's indicate this is 5.4. So the formula breaks down as change in EK plus change in EP, right? Now we've identified that the only non-conservative force acting here is the frictional force. Note that your normal force and also your FG, those are conservative forces. They're not non-conservative, they are conservative. So here, this one will only just be FK, delta X, and then cos theta. And then this one will break down to half M, and then bracket VF squared minus VI squared, and then plus mg, and then bracket height finally, minus height initially, right? Okay, so now once we have that, we can see that our struggle here is that we don't have Fk and we also don't have delta X. But then with delta X, it's not a train smash because we already know the trick from trigonometry to say that if we want to calculate delta X here, we can just use the trig ratios, right? Specifically sine. So we can just go with sine theta is equals to opposite over hypotenuse, which the opposite of this would be that. So basically the formula goes as sine theta is height over delta X, because your opposite will be the height and then your hypotenuse will be the displacement. So substituting in here, the angle for the incline is 40. So this is going to be sine 40 degrees, and then the height is 2.8, and then we are looking for delta X. Now at this point, we understand what must be done. So it's delta X is equals to 2.8 over sine 40 degrees. And obviously, you have umshinwe ibalo, aka calculator. You're just going to punch that into your calculator, 2.8 over sine 40 degrees, right? And then when you punch that into your calculator, you get 4.356. Let's just maintain at least 3 decimal places so that we are not far away from the true value. So remember, rounding off before the final answer is discouraged, right? You always have to round off to 2 decimal places in your final answer. So within the question, try to keep 3 or 4 decimal places so that you are not really far away from the range of the answers that you should get. Okay, now we have that, and then for now we can then say our delta X is that, but then also we have a problem with Fk. We must find the magnitude of the kinetic frictional force, right? But then note that if you are to refer to my video on Newton's second law also, I will drop a link for that one. So there's 2 videos that you really need to watch when it comes to understanding this whole concept. It's the video I dropped on work energy and principles, work energy and power, and then also the video that I dropped on Newton's second law. So you really need to check those ones out, because remember, I keep on mentioning that work energy and power is just an extension of Newton's second law, right? So okay, now we have that. To calculate Fk, we are going to say Fk is the product of the coefficient multiplied by the normal force. So product of coefficient and the normal force. So this is going to be 0.112. But then note that the normal force on an incline, this is case number 4, right? So I want you to check case number 4 on that video, whereby we normally say that the normal force on an incline will be equated to what? To mg cos theta. Remember, when we break down our components, the normal force on an incline usually aligns with mg cos theta, which is your Fg perpendicular, right? So here we are going to have 0.112 and then multiply that by the mass, which is 70, and then times 9.8, and then cos what? Cos the angle is 40 degrees, right? And then you're going to punch this into your calculator. 0.112 multiplied by 70 multiplied by 9.8, and then cos 40 degrees. Okay, then all of this will give you 58.85, and then, okay, let me say 567. So I'm trying my best not to round off too much. So, okay, now we have FK now and also delta X. So that means I can substitute in here and say this is 58.8567. So now I'm substituting into this formula, multiplied by 4.356, and then cos 180 degrees. We know that when it comes to the angle between the force and the displacement of an object with kinetic frictional force, it is always 180 degrees, because we say frictional force does negative work, right? So this is half. The mass is 70, and then we have our final velocity, which is what we are trying to calculate at the lowest point, and then our initial velocity 0.35, right? Remember, we are given there. So this is plus this here, which is 79.8, and then our height finally at this point, remember at this point it will be at ground level. So height finally is 0, but then height initially as it was there at that position is 2.8, right? So at this point, you just need the 8 of your calculator. So punch all of this, 58.8567 multiplied by 4.356, and then cos 180 degrees. So this here will give us negative 256.3797852. Right, so let me just write all of it. And then what is half of 70? Half of 70 will be 35, and then VF squared. Now let me do this part here. So that's 70 multiplied by 9.8, and then bracket 0 minus 2.8. Right, so this will give us negative 1920.8. Now I can take this and transpose it over to this side. So in my calculator, I'll just press negative 256.3797852 plus 1920.8, right? And then this is going to give me 1664.42015 is equals to 35 VF squared, right? Then we can divide both sides by 35 like this. And then VF squared becomes what? So that divided by 35, that's 47.55486.328. And then I can just square both sides like that. And then my final velocity, so square that square answer, it's going to be 6.896. So now when I round off to 2 decimal places, that can be 6.90 meters per second, right? So even if you try to round off to 3 or 4 decimal places, you're going to end up having an answer similar to that. So 6.90 meters per second, right? And then that's how you could have tackled that 6 marks there. So note the nature of a 6-mark question is this. You are looking for a particular value, which in this case was the final velocity, but then you had to go through some trouble of finding other quantities, right? So that's always the nature of a 6-mark question. Whenever you get something that is 6 marks, it's not showing the level of difficulty, but then the process that you have to go through. Remember, you had to get delta X and then FK before you can actually calculate the final velocity. So that's basically what you need to understand with these questions. Okay, then 5.5 says the angle between the horizontal and the slide is increased, right? So if you were to think about it, it's more like now this is moving from 40 degrees and let's say hypothetically to like 60 degrees, right? So they're increasing the angle. Now, how will the change influence the frictional force acting on the passage? Now, if you can even think about it, if you were to place an object and let it slide on its own accord at a slope that is like 40 degrees, And then now you increase the angle, it's like 60 degrees. You can even do an experiment, just like increasing the angle. Maybe you have a table and then try to increase the angle, or with your ruler there, try to put an object, maybe a pencil on top of the ruler and see what happens. Now, what you will observe is that the more you increase the angle, the more you lift up your ruler or whatever it is that you're going to use, the faster this becomes, right? The object that you will place here will be much faster. Now, if it's faster, that means it's because friction is low, right? So basically what you will realize with this relationship is that the more you keep on increasing the angle, the more you keep on increasing the gradient of the slope, it's the more the object will be faster moving downward. So which means friction is becoming lower and lower. So in other words, we can come up with the relationship that friction is inversely proportional to the angle. So the bigger the angle, the lower the friction. But then here, this is how you must explain this, right? So I haven't came to the answer. Usually with this question, I rather first explain and then I give the answer afterwards. So I will say an increase in the angle, an increase in the angle decreases the magnitude of the normal force. The magnitude of the normal force, right? So that's number one. So an increase in the angle decreases the magnitude of the normal force. Now, if the magnitude of the normal force decreases, according to this, according to the formula, according to Fk is equals to mu k times n, friction is directly proportional to the normal force, for a constant mu k, coefficient of kinetic friction. Now we know that mu k will always remain constant because the only way you can change the coefficient of friction is if you change the surface altogether, right? So the mu k relates to the material or the texture of the surface. So you can't change the coefficient of friction by simply increasing the angle or decreasing the angle. You can only change the coefficient by simply changing the whole surface and then changing the material of the surface. So according to Fk is equals to mu k times n, if this remains constant, then we know that friction will be directly proportional to the normal force for a constant mu k. And then which means a decrease in normal force, will decrease the what? Will decrease the frictional force, since we say that directly proportional. Will decrease the frictional force. So now to answer our question, what are we going to say? Decreases. And then just like that, we have our thing there. Okay, so that's how you could have tackled this question, all for 15 marks. So make sure that you come back here to this video and try to understand the approach that I took into answering all this. Okay, so now let's look at another question, right? So remember, we are on a marathon, so we're going to do as many questions as we possibly can, hopefully until I get tired. So they say, question 5, learners conduct an experiment to determine how the initial kinetic energy given to a trolley affects the distance. The trolley moves on a rough horizontal surface. A learner pushes a trolley of unknown mass until it reaches point A with kinetic energy EKA. So they say the horizontal surface delta x traveled by the trolley before it comes to rest is then measured. See the diagram below. So we can see the diagram right there. And then they say the experiment is repeated with the trolley moving on the same rough horizontal surface, but with different initial kinetic energies at point A, right? Okay, so we have a graph there indicating all of that. And then we are given questions right there. So they say ignore the rotational effect of the wheels of the trolley. 5.1 says what? Draw a labeled free body diagram showing all the forces acting on the trolley during its motion after passing point A, right? After passing point A. Okay, so now this is 5.1, right? And then for 3 marks, we must draw 3 forces. So obviously, assuming that the trolley is moving in that direction, this would be the normal force, the gravitational force, and that side would be the frictional force. So we have normal force, gravitational force, and kinetic frictional force, right? So for 3 marks, that's the forces that we should indicate there. 1, 2, 3. Okay, then name the independent variable in this experiment, right? Now we normally know that the independent variable is the one that we find on the x-axis, right? So this is the independent variable, and the dependent variable is normally the one we find on the y-axis. So we are looking for the independent variable. We're just going to say it is the what? The initial kinetic energy. The initial kinetic energy. Okay, then that's it. Okay, then just like that, we have 3, 1, and then that's 4 marks. Now let's look at this one. State the work energy theorem for 2 marks. So this was just a giveaway. Now remember, I said with the work energy theorem, you always have to remember the formula. W net is equals to change in EK. Then from this formula, you can remember the definition. It states that the net work done on an object is equal to the object's change in kinetic energy. So that's it. So the work energy theorem states that the net work done on an object is equals to the object's change in kinetic energy. Okay, right. Now, what's the next question? It's now saying, calculate the mass of the trolley if the coefficient of kinetic friction between the wheels of the trolley and the rough horizontal surface is 0.18. So note that. So for 6 marks here, we are given that. So at this point, we have already half the marks. That's 50%. So now we are fighting for some of the marks right there, right? Or as we know, we must get all the marks. Now, this is a horizontal surface. And then with the horizontal surface, I normally said the one that works best is W net formula. And then also the fact that you are given a hint here. In 5.3, they just asked you to define the work energy theorem. And then a question below says, obviously calculate the mass, which of course you will need to use energy principles. So it's given that it's a horizontal surface, and then they just ask you to define the definition for work energy theorem. Now that's enough a hint to show that you need to use that formula. So W net is equals to what? Change in EK. So we are looking to calculate the mass. We know that the mass will be from this one here when we break it down. So, okay, W net, note that from the free body diagram that we drew, we had Fk on that side and then Fg here. And then this is normal force. Now, I want you to understand this, right? So this is what we have here. If we are to use the W net formula, understand the fact that Fn, work done by Fn will be what? 0 joules, mainly because Fn will be perpendicular to the displacement. And then the work done by Fg will also be 0 joules, right? Because as we can see again, this is what? This is perpendicular to the displacement. Okay, so if we are to use this formula, this is W net is equals to change in EK, right? Note that we have this here. So to calculate, we can simply say, let's have our W net formula and then break it down now to what? Let's break it down to EK finally minus EK initially, since we are given this, right? And then our W net will only be represented by what? By Fk here. So this will be Fk and then delta X and then cos theta. But then we are given a coefficient here of 0.13, which we do already know that if we are given the coefficient, that means we must calculate Fk on our own, right? So now considering this, we can consider that our Ek finally will be what? So Ek finally can be, let's look at this. So these are the initial kinetic energies and then all the way like that. So obviously, because this is this trolley will be moving all the way up until it comes to a stop, right? So it will be moving all the way up until it comes to a stop. Then because they said here, by the trolley before it comes to rest. So that means when it comes to rest, our kinetic energy will be 0, right? If we are to take this one, the maximum initial kinetic energy, because remember, these experiments are being done with the first one, it's given an initial kinetic energy of 6. The second one is given an initial kinetic energy of 12. And then now they do the experiment for the third time. And then with the maximum initial kinetic energy that they can possibly give, which is 18. So here we are much more focused on that one. So which is the Ek initially will be 18. Note that all of these values that you are given here are initial kinetic energies. So if I'm going to use the 18, that means the 18 must correspond with the 4.5. If in your case you decide to use 12, the 12 must correspond with the 3.0. If you decide to use 6, the 6 must correspond with what? With the 1.5 for the distance. So note that if you take an initial kinetic energy of some sort, it must correspond to the displacement that it covers, right? So I think we are good on that part. Now, we still have the problem of Fk. Haven't calculated Fk, but then we know that Fk is what? Mu k multiplied by the normal force. But then from here, from our free body diagram, this is case number 1. It's just moving horizontally. And then we know that normal force will be exactly the same as the gravitational force. Not mg cos theta this time, just mg. So this is, we know that normal force will be equals to Fg. So that means we'll have mu k multiplied by the mass times the gravitational acceleration. Remember that Fg breaks down to mass times g. So the coefficient, we are given 0.18. And then the mass of, that's what we are looking for, right? So it's m. Then multiplied by 9.8. Very interesting question. So 0.18 multiplied by 9.8. We are going to have 1.764. 1.764 m, right? So that is our value for Fk in terms of m, because we are looking for that mass. So we're just going to substitute it the way it is. So don't dazzle, just zazazel. Trust the process. Then our delta x is what? 4.5. And then remember, anything to do with theta on Fk should be 1/8, right? So angle between the displacement and the force, kinetic friction, is 1/8. So because it does negative work. 0 minus 18, that's negative 18. And then let's punch this into our calculator. Your calculator, you're going to have 1.764 multiplied by 4.5 cos 180 degrees, right? So basically, you just punch all of this. This will give us negative 7.938. You still keep the m is equals to negative 18. So now to calculate, you will then have to divide both sides by that. So if I can just divide both sides by negative 7.938, negative 7.938, then my mass is, so let me see, negative 18 divided by that negative 7.938. This is going to give me 2 decimal places, that's 27 kg. Note that the SI unit for mass in physics is kg. Paper 1, it's in kg. Paper 2, it's in grams, right? So, okay, that's it. 2.27 kilograms. And then that's how you could have got that 6 marks. So as you can see again, we are trying to calculate the mass, but then we needed to have Fk in terms of m first. So it's also a nature of a 6-mark question. Before we can calculate what we are looking for, we need to be calculating something on the side that we need to actually substitute into the formula, right? So that's basically how we go about it. Nice. Okay, pretty interesting question, this one. Very different from the others. Let's see what else do we get. Do we have? Okay, question 5. A constant force F is applied at an angle of 30 degrees to the horizontal on a crate of mass 6 kg that is initially at rest. Note that initially at rest, meaning the initial velocity is 0. As shown in the diagram below, a constant frictional force of 10 Newton. So hallelujah, this time around we are given frictional force. Then act on the crate as it moves from rest at point A along a horizontal surface to point B. The distance between point A and point B is 1.5 meters. The speed of the crate at point B is 2 meters per second. 2 meters per second. Then define the term work done by a force. Now, what is work done? We say work is the product of the force and the displacement of an object, right? So it's the product of the force and the displacement of an object. So it's just a multiplication of the force and the displacement of a particular object, right? So that's basically how you would define that one, right? Then let's now proceed. 5.2 says, draw a label free body diagram showing all the forces acting on the crate as it moves, right? So 4 marks, 4 forces. So we're just going to start there and then dot to indicate the 6 kg block. And then you want to start with the obvious forces. Gravitational force always acting downward, normal force always perpendicular to the surface, and then the force is being applied in that direction. So you just put it the way it is here. And then obviously, since this is a rough surface, there will be frictional force that opposes. Note that the frictional force does not oppose the force applied. It opposes the motion of an object. This is moving horizontally. The block, as much as the force is being applied at 30 degrees, the block is not being lifted up. The block is moving horizontally, and therefore Fk opposes that horizontal motion. Remember, what is frictional force? It is the force that opposes the motion of an object. So this is force applied, this is a normal force, and this is gravitational force, and this is kinetic frictional force. And then that's how we have that, right? So if you want, you can even indicate the angle here. So, but then it's not necessary. Okay, then now we have how many marks? 6 marks, 6 out of 12. That's 40% at this point, right? So note that we are collecting marks. Then using energy principles only, calculate the magnitude of F. Calculate the magnitude of F. Now, this is a horizontal surface, so you do know that I'm going to opt to use W net, right? I am definitely going to opt to use W net. And then we know that the normal force does not do any work. Work done by normal force will be 0 joules. Work done by Fg will be 0 joules, mainly because they are perpendicular to the displacement, right? So no work done by normal force, no work done by gravitational force. So that means the only 2 forces that are doing work on this 6 kg block is the force applied and the Fk, which they are going to be the ones that I represent on the W net formula. Okay, 5.3. W net is equals to change in Ek. So we're going to say work done by force applied plus work done by Fk. Remember, we are trying to calculate that force applied, that F. So which is, this one breaks down to, let me just write change in Ek, so that when I break down everything. So this is force applied delta x and then cos theta plus Fk delta x and then cos theta. And then this is half mass Vf squared minus Vi squared. Now I want you to note something with this one, right? I want you to be very careful with this one. So here we have, we're going to break it down to what? Fa is, what is the force applied? That's what we are looking for. And then what is the displacement? They say it covers 1.5 meters going from point A to point B. So I'm going to put 1.5. But then when it comes to the angle, note that the angle between the force and the displacement will no longer be 0 degrees here because the force is being applied at an angle, right? So if the force is being applied at an angle, we will consider that if this is our displacement here, because the object is moving to the right. So let's say this is our displacement. Now the angle between the displacement and the force in question is now what? 30 degrees. Again, on that video, I do mention that if the force is being applied at an angle, what you consider here at theta is the angle at which the force is being applied, right? So we are not going to put 0 this time around. We are going to put 30 degrees, right? Then we have our Fk, which they said is what? 10 newtons. So we have 10, and then here it's 1.5, and then we have cos what? Now, the 30 degrees only applies to that applied force. But then for here, we still continue with our 180 degrees because as we know, Fk opposes the motion, right? And then it forms that angle on a straight line with the displacement because remember, Fk is moving in that direction. So if you can check here, the angle between the displacement and Fk is exactly 180 degrees. So this is equals to half. The mass is 6. Final velocity, they said is 2 meters per second. And then it was from rest, right? So 0, and then square. So now at this point, you need the aid of your calculator. When I say 1.5 cos 30 degrees, and then this is going to give you what? 1.299 and then F. So let's keep it to 3 decimal places at least. And then 10 multiplied by 1.5 and then cos 180 degrees. So, okay, here we have negative 15, right? So the F that we are talking about is for the force applied. And then it's equals to what? Punch that's half and then 6. And then we have 2 square minus 0 square, close bracket. And then this is going to give us 12. Now we can take the negative 15 over to this side. That's 1.299F is equals to 12 plus 15. If we transpose it, changes the sign. Then we have 27 for Mandela. 1.299 and then 1.299. So this is F is equals to 27 divided by 1.299. So this is going to give us 20.79, right? Or yes, 2 decimal places, 20.785. So that's 79 newtons. Hallelujah. And then that's how you would have calculated that one. So, okay, so use the WNet formula because we are dealing with a horizontal surface. But then the one thing that you always have to note here, the angle, the force was being applied at an angle. So that means we needed to consider that our theta there becomes the angle, right? The angle in which the force has been applied. So that's the angle between the displacement and the force. Okay, so very crucial to note. Then 5.4, a 2 kg object is placed in the crate. What effect will this have on the work done by the same force F when the crate is again moved from point A to point B? Right? Only increase, decrease, or remain the same. So a 2 kg block is placed in the crate. So that means they are adding on to the mass of this one. What effect will this have on the work done by the same force when the crate is again moved from point A to point B? Now, if you can check this, I want you to check this. So work done by force applied breaks down to what? The force applied, delta X, and then cos theta. This has nothing to do with the mass. If I'm applying the same force, and then I'm also moving it over the same distance or displacement, then definitely the work done by that force applied must remain the same, because the fact that they added on the mass does not change anything. I'm still moving it at a distance of 1.5 meters, and then I'm still applying the same force, right? Only thing that will change is that probably this time around it will take much more time, right, for me to actually pull it from A to B. But then basically it will still be the same work done by that force. And then for 5.4, it will just be remains the same. Remains the same. So with this formula, there is no mass. As you can see with this formula, there is nowhere where we consider a mass. So the work done by the force applied is independent of the mass. Okay, so now let's move. So 12 marks in the bag, just like that. Okay, so we have another question here. It says an object with a mass of 85 kg is initially at rest. Check that one out. Initially at rest on the ground. It is then pulled vertically upwards at a constant acceleration. Note that it's not constant velocity, it's constant acceleration. So that means acceleration is not zero. As we can see, acceleration is given. So 0.75 meters per second square by means of a light inextensible rope, as shown in the diagram below. Ignore air resistance, the mass of the rope, or any rotational effect. So ignore air resistance, the mass of the rope, or any rotational effect. Then 6.1 says, draw a labeled free body diagram for the mass while it moves upward. 2 marks, right? So what are the two forces that are here? We know that it has to be what? It has to be the gravitational force acting downward, and then it has to be the tension force acting upward. Now, obviously, because this is going upward, we're going to assume that the tension is a bit longer than the gravitational force, right? So that's in your free body diagram, it would be crucial for you to actually differentiate the lengths of these two. So your tension force make it a little larger than the gravitational force to indicate that your pulling force upward is much greater than the force of gravity downward, right? So, okay. Then that's basically that. So maybe in your exam, they would not really pay attention to that. But then, yeah, sometimes maybe just to be safe or to know, and always note that if it's going upward, it's because the tension force usually is greater than the gravitational force. Then 6.2, name the non-conservative force acting on the mass. The what? The non-conservative force. Cannot be gravity because that's a conservative force, but it's definitely tension. Remember your examples of non-conservative forces: frictional force, tension, and applied force. So it's definitely tension force. Right. And then now they say calculate the work done on the mass by the what? Gravitational force when the mass has reached a height of 11 meters. Now note this, for 6.3, you will note that the object is going upward as indicated by the arrow. And then even here, they said it's pulled vertically upwards. So this is the positive direction. This is the negative direction. Now, I want you to note this. We normally say that work done by Fg is 0 joules, right? So you've been seeing me in all these questions. Work done by Fg is 0 joules. But I need you to be careful when an object is moving vertically. Remember, we normally say it's 0 joules if the object is moving horizontally. So the object will be moving horizontally, but the Fg will be acting vertically. So the object is moving horizontally, meaning that's the displacement, but then Fg is moving downward like this. So what's the angle between Fg and the displacement? 90 degrees. But this is a different case here. Where is the object now moving? It's moving upward. So there is the displacement, delta x. Now let's look at Fg. Fg is still moving vertically downward. So this is vertical and this is vertical. Now you can see that the angle that will be formed between Fg and delta x here will no longer be 90 degrees. It has to be what? 180 degrees, because let's look at the displacement. Let's look at FG. Now we can see that the angle that they form here is an angle on a straight line, which is 180 degrees. So note that FG, this point around, it does work. It's not 0 joules. So work done by FG here is not 0 joules, mainly because we can see that it's now forming an angle of 180 degrees. And then it's only 0 joules if it forms an angle of 90 degrees, if it's perpendicular to the displacement. So do not memorize that it's always 0 joules. In this case, this is a different case because FG is moving vertically and your object happens to be moving vertically as well. So this would be work done by FG is equals to mg, because FG breaks down to that, and then delta x cos theta. So our mass would be 85, 9.8, or delta x 11 meters, and then cos what? 180 degrees. Now, when you calculate, you will get a value for work done by FG. So let's put that in our umshini ibalo. 85 multiplied by 9.8, and then multiplied by 11, and then cos 180 degrees. So this is giving us negative 9,163 what? Joules. And then for 3 marks, that's what we have. So formula substitution into the formula and the correct answer. So very crucial to note that one, right? So it's a revelation that I am giving you to say that do not memorize the fact that work done by FG is always 0 joules, right? So in a vertical moving object, that is not the case. Okay, then 6.4 says, state the work energy theorem in watts. So again, with this one, we know W net is equals to change in EK for us to remember the definition. And then we just say, state that the net work done on an object is equal to the object's change in kinetic energy. In kinetic energy. So it states that the net work done on an object is equals to the object's change in kinetic energy, right? Then we have it like that. So 2 marks. So how many marks have we collected so far? 3 plus 3, that's 6, then plus 2, that's 8. And then all of this is out of 19. Okay, so a luta continua. Use the work energy theorem to calculate the speed. You see this one specifically saying use the work energy theorem. So even if you wanted to use WNC, you can't with this one. It's specifically telling you to use this particular theorem. Use work energy theorem to calculate the speed of the mass when it is at a height of 11 meters. So that means we're going to start by saying W net is equals to what? Change in EK. So we want to calculate the mass. Now the two forces that we have are tension and FG, as we saw. So we are going to have work done by work done by tension and all that. So okay, let's see. So do we have tension, or can we calculate tension? So okay, we can actually calculate the F net. So if we can actually do this, let's see. With the F net, we can say F net is equals to what? M times A, because we already have the acceleration. And then this is 0.85 multiplied by 0.75, right, from Newton's second law. And then note this, bear with me. This is 85 multiplied by 0.75, which is what? 63.75 newtons. But then remember that W net can break down to what? If we just want to calculate it straightforward, this is F net, we can actually break it down to F net, delta X, and then cos theta. Now we are doing this because we actually don't have the value for tension, right? We only have the value for Fg. So in order to then calculate, without having to calculate the value of tension, we can just say we are already given acceleration. So why not just calculate the F net and then actually do the work done by the net force just by having the F net there, right? The magnitude of the net force. So just like that, we have 63.75, and then the displacement it covers is 11 meters. But then when it comes to the theta, let's look at where the object is going. Obviously, the object is going into the positive direction, whereby it is parallel to what? To the displacement. So if it's parallel to the displacement, then obviously the theta is supposed to be 0 degrees. And then here we can have half. Remember, we are trying to calculate what? Mass. So we're going to find the mass from this side, and then Vf squared minus Vi squared. So we have 63.75 multiplied by 11, and then cos 0 degrees, which is going to give us 701.25. And then here, let's substitute in. We have half. The mass is 80. Okay, so we are trying to calculate the speed. Okay, what did I read? Calculate the speed of the mass. So 85. Sorry for that. We are not calculating the mass. The mass is already given. We are calculating the speed when it is at a height of 11 meters, meaning the final velocity here. So initially it was at rest. And then 0 square. So we have 701.25 is equals to half of 85 is what? Should be 42.5. And then here we have Vf squared. Divide both sides by 42.5. And then 42.5. We are going to have Vf squared is 701.25 divided by 42.5. And then that's 16.5. So I hope that you are doing these questions along with me. You have your pen and your notebook, and then you are working out these questions along with me, and then verifying everything that I am saying here, punching it into your calculator so that you actually get to learn. So do not consume these videos passively, but then make sure that you treat it as if you would your teacher at school. And then whenever they speak, you try to jot down everything that they're saying. So that's how it works best. That's how you learn, right? So you learn by doing. Then, okay, final velocity is 4.06 meters per second. So that's it. Now, let's get to 8.6. So this is a power question. They say a 30 kilowatts motor is used to lift the mass of 85 kg to this height of 11 meters. Calculate the percentage efficiency of this motor if it is working at maximum power. So we want the percentage efficient. So that means the 30 kilowatt is probably the maximum power that it can supply. But then obviously not all of that power will be at work, right? So we are trying to find that if it's working at that maximum power that it's going to be working with, what's the percentage efficiency compared to the total power that it can actually supply, right? So, okay, now what we can do with this one is that we consider that our formulas for power is W over delta T, or we can have the one for P is equals to F V average, right? So this one, normally I prefer if we are given the average velocity, but since nothing is being said about the velocities here, or except that we did calculate the velocity here, so maybe that one might also work as well. But then, okay, let's try to do it with this one. So I can just decide to calculate the work done by the motor, since we are speaking about the motor, and the motor acts as a what? As a force applied, right? As the applied force. So considering this an energy principle, I can start by doing W net, and then it's equals to change in EK, right? Now I do realize that there will be what? There will be that resistance in the force, So we have negative. So they say a 90 kilowatt motor is used to lift the mass of 85 kg to this height, right? Of 11 meter. Calculate the percentage efficiency of this motor. So obviously it's this one that we considered. So the motor acts as that. And then obviously we know that gravitational force is this. So it's now a motor that is pulling this. Remember, there is a rope and then there is a motor pulling from upward here. So this is the force of the motor. All of it, let's just define it as the force of the motor. And then work done by motor plus work done by the gravitational force will be equals to what? The change in EK, which is breaks down to, let me just write change in EK for now. So work done by the motor, we don't know. But then we did calculate the work done by FG somewhere. And then we got what was the value? Negative 9,163 joules, right? So if you have kept it from this question here, 5.3, which is why I'm saying that it's crucial that you actually get to write these questions. So half m and then vf squared minus vi squared. Okay, so now we have work done by the motor minus that 9,163 is half. We have 85 here. The final velocity is the one that we calculated, which is 4.06 square, and then minus 0 square. And then work done by the motor will be equals to minus 9,163. If we punch all of this into our calculator, let's see, to calculate the work done by the motor. So that's 1/2, 85, 4.06 square minus 0 square, then close the bracket. Then we have a 700.553. Then let's transpose this over to that side. So that's that value plus 9,163. So this gives us work done of 9,863.553 and then joules. Now that means I can then use this formula, which is power is equals to work done by the motor over delta T. So work done by motor, then that's 9,863.553. So that's 55. Then what's the time? Are we told the time that it took for it to be lifted over there? So we can actually find the time by using an equation of motion because we are given acceleration. So, wow, Vf Vi plus A delta T. Our final velocity is 4.06. Our initial velocity is 0. And then acceleration is A. Delta time is what? That's what we are looking for. Acceleration, remember, we are given. There is it, 0.75. And then delta T. 4.06 is equals to 0.75 delta T. Can then divide both sides by 0.75. 0.75. Then our delta T becomes what? So let's punch that into our calculator. 4.06 divided by 0.75. So this is a true 6-mark question. 5.413 seconds, right? And then we can just use it here. 5.413. And then therefore our power becomes what? Let's see, 9,863.553 divided by 5.413. And then this becomes 1,822.197. 197. And then this is what I'm going to do now. Going to take this, and then remember, I'm still calculating the what you call the power efficiency. So to then calculate that, I would then need to come here and say, yeah, this was a very, very long question. It was a stretch. So in order to calculate that, I can now say a percentage efficiency of this is to take this power that I've just calculated, 1,822.197 over the 30 kilowatts. Now, kilowatts means that I need to multiply that by 1,000. So that becomes 30,000. And then multiply that by 100 because it's the percentage efficient. So it's the power that the maximum power over the power that can generally be supplied, then multiplied by 100. So we have 1822.197 divided by 30,000 and then multiplied by 100. We find that the percentage efficiency will be 6.07%. 6.07%. There we go. So, yep, a very, very nice 6-mark question. A very nice one. A very nice one. This one, yeah. This one was from deep in the pits of hell. Okay. A breather. Now, let's go to another question. Okay, so we have this one here. It says a car of mass 2 kg is traveling with an initial speed of 1.5 meters per second when it is pulled by a horizontal force F of unknown magnitude over a distance of 2.5 meter, and then a frictional force of 26 Newton acts on the car as it moves. The car reaches a speed of 4 meters per second. And then a 5.1.1 says, state the work energy theorem, right? State the work energy theorem. Again, W net is equals to change in EK. And then this helps us to remember work energy theorem states that the net work done. So if you want to remember definitions, work with as many questions as possible. You will keep on seeing the very same definitions. You write them every time you see them, you write them. That's how you'll end up just knowing those definitions. States that the net work done on an object is equal to the object's change in kinetic energy. So states that the net work done on an object is equals to the object's change in kinetic energy, right? And then that's how we go. Then 5.1.3, using energy principles, calculate the magnitude of force F. We just defined work energy theorem. So obviously, if they're saying use energy principle, the closest energy principle that we can apply is obviously the work energy theorem, right? And also considering that we are working with what? A horizontal force. A horizontal airplane, a horizontal surface, right? So this is a horizontal surface. Now, let's check. Are we given any magnitude of the frictional force? Is there any friction? A car of mass 2 kg or a frictional force of 26 Newton. We should have highlighted that. And then the car reaches a speed of 4 meters per second. Okay. So that means I can start my calculation with the W net formula, 5.1.2. W net is equals to change in EK, right? And then this will break down to work done by force applied plus work done by kinetic frictional force, and then which is equals to change in EK. Then break it down to force applied delta X and then cos theta plus Fk delta X cos theta is equals to half m bracket Vf squared minus Vi squared. Now, if we are to draw a free body diagram, indicating all the forces acting on that block, then we understand that we are going to have normal force, and then down here we are going to have gravitational force. And then on the side there, this here we have the force applied in that direction, and then opposing the motion of an object is the kinetic frictional force. Because this is moving on a horizontal surface node, and then the objects are acting vertically, the forces are acting vertically, that means perpendicular to the displacement. So work done by Fn, 0 joules. Work done by Fg, 0 joules this time around, because we are working with an object that is moving horizontally, but those two forces are being applied vertically to be perpendicular to the displacement, forming an angle of 90 degrees with the displacement, and therefore the work done by those two forces is 0 joules. Okay, then a force applied, we don't have it, so it's just F, and then the displacement 2.5. Then we have cos what? Now, obviously, this is in the same direction as the displacement, so the angle is 0 degrees. For Fk, we have 26, and then displacement, still the same 2.5, and then cos what? 180 degrees. So this is equals to half. The mass is 2 kg. The final velocity, they say the car reaches a speed of 4 meters per second. So 4 squared. And then here we have 1.5. So the initial speed is 1.5. 1.5 square. Okay, so now you have 2.5 cos 0. That will give us 2.5 F. And then we have 26 times 2.5 and then cos 180 degrees. So this is negative 65 is equals to half, and then here we have 2, and then we have 4 square minus 1.5 square, close the bracket. So this is going to give us 13.75. So that's 2.5 F is equals to 13.75. If we transpose this plus 65, and then is equals to what? 78.75. Then we can divide both sides by 2.5. 2.5. Then just like that, we have our magnitude of the force applied. Then divided by 2.5. That's a 31.5 newtons. Yes. Hallelujah. Okay, so that's basically how you would do that question right there. Okay, so nice. For 4 marks, you just needed to apply the WNet formula and then simply just trust in the process up until you get to the magnitude of force F. Okay, then let's proceed. They say a windmill on a farm is used to pump stationary water from point A in a well. The water flows past point B, 35 meters above point A at a speed of 2.1 meters per second. Then 5.2.1 says define a non-conservative force. So what is a non-conservative force? Do not be lazy to define, right? So define it as many times as possible until it always rings in your mind, right? Define a non-conservative force, we say, is a force for which the work done in moving an object between 2 points, depends on the path taken. That's it. So a force for which the work done in moving an object between 2 points depends on the path taken. We know that as what? The non-conservative force. Now 5.2.2 now says the pump in the windmill is rated 500 watts, right? Calculate the mass of water air flowing past point B every minute. Now, every minute means what? For 60 seconds. Because remember, when we are doing this formula, P is equals to W over delta T, then we know that our delta T should always be in seconds. So obviously, we must use energy principles. But then above here, we have been told to define a non-conservative force, which means we might as well treat this W as work done by non-conservative force, right? So, okay, we know that there's the force of the pump, and then obviously there's gravitational force. But then obviously the power is being given by the pump. So force of pump, and then here we have the gravitational force. The power comes from the pump. So we can calculate the work done by that pump by saying power is what? 500. And then here we have work done by pump over delta T, which is 1 minute, 60 seconds. So work done by the pump will now be what? 500 multiplied by 60. So that's 30,000 watts. SI unit is very important. So watts. And then now we have that. This is what we must consider. The pump is a non-conservative force, right? Work done by the pump is a non-conservative force. So we can say this will be equals to change in EK plus change in what? EP, which means that I have to put the 30,000 here and then break this down to half mass bracket final velocity square minus initial velocity square plus mg bracket height finally minus height initial. So we have the 30,000 and then this is half. The mass is what? 2 kg. And then final velocity from point A, stationary water, velocity is 0 to a speed of 2.1. 2.1 square minus 0 square plus we have 2 multiplied by 9.8. The height finally, when it reaches point B, is 35. The height initially, it's still on ground level or underground level. Then 35 minus 0. So, okay, now we have 30,000 here. And then this is 1 over 2. 2 here, bracket 2.1 square minus 0 square. Close the bracket. So this is 4.41. And then right here. Wait, what are we looking for? Calculate the mass. Oh, look at me. I'm busy using the mass of that one. Oh, man. This is this is really a fatigue playing with me. Okay. So I guess this will be the final question that I do. Then mass. Okay, so I am calculating mass. So I must not use the mass from that one. So, yep. Half, we're going to have half. And then multiplied by 2.1 square. Glad I picked that one up early. So that's 2.205 m. And then here I have 9.8 multiplied by 35. So that's plus 343 m. So these ones are like terms. That means I can just add them all together and then have 2.205 plus 343. And then this is 345.205 m. And then I can divide both sides by 345.205. 345.205. Then let's calculate the mass. We are going to say 30,000 divided by that. So which will give me 86.90 kg. Right. So that's it, rounded off to 2 decimal places. So that's how you were supposed to go through this question. So yeah, make sure that you come back to this video. Watch it as many times as possible. Try to understand the approach that I took into solving these questions. So I'm still going to do more videos, more long videos as you requested, 1 hour and more of just those videos where I just target as many questions as possible, for each and every topic, both maths and science. So I'll just commit to doing as many questions as possible. And then, yeah, just to make sure that you get that fire content, and then you are ready for your June exams, your prelim exams, and most importantly, your final year examination. Right. So with all that being said, press that subscribe button, share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.